Hi students, I am Sheeba from EC Department, Emmanuel Research JJ College of Engineering. Today we are learn about the topic integrator and differentiator from Unit 2. Two of the most fundamentally important mathematical operations are differentiation and integration. The operational amplifier can be used to perform either of these operations. First, we can see the integrator. A circuit in which the output voltage waveform is the time integral of the input voltage waveform is called an integrator or integrating amplifier. Integrator produces a summing action over a required time interval, and the circuit is based on the general parallel inverting voltage feedback model. Next, ideal integrator. The ideal integrator circuit is obtained by using a basic inverting amplifier configuration with a feedback resistor RF is replaced by a capacitor CF. The current through the capacitor IC of t equal to C into dVc of t by dt. Va of t minus Va of t divided by R1 equal to Cf into d by dt of Va of t minus V0 of t. However, Vb of t equal to Va of t equal to 0 because the gain of the operational amplifier Av is very large. Therefore, Va of t by R1 equal to Cf d by dt of minus V0 of dt. This is the diagram of ideal integrator. Integrating both sides with respective time, we get the output voltages defined by integral 0 to t Va of t by R1 into dt equal to integral 0 to t Cf into d by dt of minus V0 of t into dt equal to minus Cf V0 of t plus V0 of 0. V0 of t equal to minus 1 by R1 into Cf integral 0 to t Va of t into dt plus V0, where V0 is the integration constant proportional to the output voltage V0 of t value at t equal to 0. In frequency domain, the above equation becomes V0 of S equal to minus 1 by S into R1 into Cf Va of S, letting S equal to j omega. In steady state, we get V0 of j omega equal to minus 1 by j omega R1 into Cf Va into j omega. Hence, the magnitude of the transfer function of the integrator is modulus A equal to modulus V0 of j omega divided by Va of j omega equal to j by omega into R1 into Cf equal to 1 by omega R1 into Cf. At omega equal to 0, the gain of the integrator is infinite. Also, the capacitor acts as an open circuit and hence there is no negative feedback. Thus, the operational amplifier operates in open loop and hence the gain becomes infinite. In practice, the output will never become infinite. As the frequency increases, the gain of the integrator decreases. This is the waveform of ideal integrator. It may be noted that there is a negative sign in the output voltage. This integrator is known as inverting integrator. For example, if the input is sine wave, the output will be a cosine wave. Or if the input is square wave, the output will be a triangular wave. Next, we can see the practical integrator. The gain of the integrator at low frequency can be limited to avoid the saturation problem if the feedback capacitor is shunted by a resistance RF. Here, the feedback capacitor is shunted by a resistor RF so that the gain of the integrator at low frequency is limited to avoid any saturation problem. Since the parallel combination of resistor RF and capacitor CF dissipates power, this circuit is called a lossy integrator. The resistor RF provides the DC stabilization by limiting the low frequency gain to minus RF by R1. The resistor R combination is given by R comb equal to R1 parallel RF, and when RF greater than R1, R comb equal to R1. At the inverting input terminal of the operational amplifier, the nodal equation may be written as VI of S by R1 plus S into CF V0 of S plus V0 of S by RF equal to 0. Rearranging the above equation, we get V0 of S equal to minus 1 by S into R1 into CF plus R1 by RF VI of S. Substituting S equal to J omega, we get the transfer function as expressed by modulus A equal to modulus V0 by VI equal to 1 by root of omega square R1 square CF square plus R1 square by RF square equal to RF by R1 divided by root of 1 plus omega into RF into CF the whole square. When RF is very large, the lossy integrator will approximately become an ideal integrator. At low frequencies, assuming the low level frequency to be FA, the gain is approximately equal to RF by R1. At 3 dB level, the gain is 0.707 RF by R1, root of 1 plus omega into RF CF the whole square equal to root 2. 1 plus omega into RF into CF square equal to root 2. Solving for F equal to FA, we get 2 pi FA RF into CF equal to 1. Hence, FA equal to 1 by 2 pi RF into CF. The frequency FE is the frequency at which the transfer function or gain of the integrator is 1 or 0 dB. 1 equal to 1 by 2 pi FE R1 into CF. Hence, FE equal to 1 by 2 pi R1 into Cf. When the input frequency is less than Fa, the circuit will not act as an integrator and it will only act as a simple inverting amplifier. When the input frequency is equal to Fa, there will be 50% accuracy. As a thumb rule, if the input frequency is 10 times Fa, then it results in 99% of accuracy. Next, the application of integrator. Integrators may be used in combination with summers and amplifiers to form analog computers which are used to model a variety of physical systems in real time. The integrator circuits are used as wave shaping circuits and used to convert square waves into triangular waves. Further, they are used for solving differential equations in analog to digital converters and RAM generators. Next, we can see the differentiator. The differentiator can perform the mathematical operation of differentiation, that is, the output voltage is the differentiation of the input voltage. This operation is very useful to find the rate at which a signal varies with time. The ideal differentiator is obtained by interchanging the position of the resistor and capacitor in the ideal integrator circuit. The expression for the output voltage can be obtained from Kirchhoff's current law written at node A as follows: IC equal to IB plus IF. Since IB equal to 0, IC equal to IF, that is C1 into d by dt of VA minus VA equal to VA minus V0 by RF. But VA equal to VB equal to 0 volt since A is very large. Z1 into dVi by dt equal to minus V0 by RF. V0 equal to minus RF into C1 dVi by dt. Thus, the output V0 is equal to the RF C1 times the negative instantaneous rate of change of the input voltage Vi with time. This is the circuit diagram of ideal differentiator. For the analysis, we get the Fa value equal to 1 by 2 pi Rf into C1. This is the waveform of differentiator. In electronic applications, the input to a differentiator is a signal which will be generally varying as a function of time. Therefore, the output of the differentiator is proportional to the rate of change of the input signal. The input signals are described by the trigonometric functions sine and cosine. A good differentiator may be designed as per the following steps. Choose Fa equal to the highest frequency of the input signal. Assume a practical value of C1 and then calculate Rf. Choose Fe equal to 10 into Fa. Now calculate the values of R1 and Cf, so that R1 into C1 equal to Rf into Cf. The time period t of the input signal is larger than or equal to Rf into C1, that is t greater than or equal to Rf into C1. Next, the limitation of ideal differentiator. When compared to integrator circuits, the differentiator circuits are more susceptible to noise. The input noise fluctuations of small amplitudes will have large derivatives. When differentiated, these noise fluctuations will generate large noise signals at the output, which will introduce a pure signal to noise ratio. This problem may be minimized by placing a resistor in series with the input capacitor. This modified circuit differentiates only low frequency signals with a constant high frequency gain. Next, practical differentiator. A practical differentiator circuit is shown in figure. This eliminates the limitations of noise and stability. The effective current at the node A is 0. The input current IC equal to VI minus VA divided by Z1 equal to VI by Z1, where Z1 equal to R1 in series with C1. Therefore, the input impedance Z1 equal to R1 plus 1 by S into C1 equal to 1 plus S into R1 by C1 divided by S into C1. IC equal to S into C1 VA of S divided by 1 plus S into R1 into Z1. The current IF1 flowing through RF is given by IF1 equal to VA minus V0 by RF equal to minus V0 by RF. Taking Laplace transform, we get IF1 equal to V0 of S by RF. Similarly, the current IF2 flowing through CF is given by IF2 equal to CF d of VA minus V0 by dt equal to minus CF into dV0 by dt. Taking Laplace transform, we get IF2 equal to minus S into CF into V0 of S. Applying Kirchhoff's current law at node A, we have IC equal to IF1 plus IF2 S into C1 in VA of S divided by 1 plus S into R1 into C1 equal to minus V0 of S by RF minus S into CF V0 of S. Similarly, V0 of S equal to minus S into RF C1 VA of S divided by 1 plus S into RF CF 1 plus S into R1 into C1. The transfer function for the circuit is given by V0 of S by VI of S equal to ZF by ZI equal to minus S into RF into Z1 divided by 1 plus S into RF into CF into 1 plus S into R1 into C1. Letting RF CF equal to R1 into Z1, we get V0 of S by VA of S equal to minus S into RF into C1 divided by 1 plus S into R1 into C1 square equal to minus S into RF into Z1 divided by 1 plus J Fi Fe the whole square. Fe equal to 1 by 2 pi R1 into C1. Equation shows that the gain increases at plus 20 dB per decade for frequency ranges of f less than fv and decreases at the rate of minus 20 dB per decade for f greater than fv. Application of differentiator. The differentiators can be used as wave shaping circuits. They can be used to convert triangular waves into square waves. Since differentiators tend to seek rapid changes in the input signal, they are quite useful as edge detectors in the FM demodulators. Thank you.